Welcome to week 11. Believe it or not, you've come to the final lab or lectures and lab lectures. So week 12 doesn't have any lectures. It's simply taking the final for the class. So that's pretty cool. You finally come to the end of a lot of work. Anyway, in week 11 we're going to be covering two distinctly different topics. In the first lecture, we're going to be finishing up lighting considerations. We're going to be looking at LED lighting. And then in the last lecture, we're going to be doing some simple financial or economic analysis. And that'll complete the lectures for the class. So this final section of LED lighting, we're going to look at LED lighting. This has really made huge strides in the last 4 or 5 years. It's still an area of lighting that's got major changes going on. Basically, an LED is a light source which uses semiconductors and electroluminescence to create light. LED stands for light emitting diode, is one of a group that includes OLED, organic light emitting diode, and EL, electroluminescence lamps. So that's the basic category. On the pro side for LEDs, energy efficiency source of light for short distances and small areas. So they're highly energy efficient if you only have one or two of them. A typical LED only requires 30 to 60 milliwatts to operate. They're very durable, shock-proof, for the most part. And again, this is comparing against incandescent, where if you hit an incandescent, most of them, because the tungsten is brittle, shatters it. They are directional in nature, so they are useful in applications for focusing the light. So you can get a little better ability to prevent light pollution or stray light in outdoor lighting. On the con side, they may be unreliable in application where there's wide ranges in temperature. They are an electronic device. They like stability. So if you have rapidly changing or wide-ranging temperatures, they don't deal as well. They are semiconductors, so they're sensitive to heat. Now, when you put a number of LEDs together to get more light out, this pattern of LEDs is called an array. So a number of LEDs put together is called an array. The minute you do this, they give off a lot of heat. So LEDs that are put in an array have to have some sort of method to dissipate the heat. Either they have to add some sort of highly conductive metal to draw the heat away, like fins, whatever, or they have to put little tiny fans in. Now, both these things have a tendency to reduce the overall efficacy of the lamp, reduce the efficiency, especially if they have little fans. The other problem with LEDs is for a long time color correction has been really difficult. So trying to get really good color rendition off of LEDs has been a trick. We're to the point now where LEDs can rival fluorescence. You can get an LED with a color rendition index of up around 80, but there's still nothing to replace incandescent as far as getting super high color rendition indexes of 90 to 100. Manufacturing quality is still in question. I'd make sure that you got your LED lamps from a reputable manufacturer. There's a lot of stuff out there that have quality assurance issues and don't have high either efficacy or lifespan because of the manufacturing inconsistencies. And they are made out of rare earth metals, which can dictate cost. And again, we're trying to get these rare earth metals for LEDs from typical countries that don't exactly like us. So we always seem to have an issue in that area. What I want to look at here is sort of give you an idea to compare like a 60 watt incandescent versus a off the shelf day one LED. So in this first slide, we're going to look at a 60 watt incandescent and compare it versus an LED replacement for a 60 watt incandescent. And we're going to compare the following areas. We're going to compare color addition index, lifespan, the efficiency, power usage, whether they're dimmable or not, and the overall cost. So in the left-hand column, you see the standard incandescent. Again, really good on the color addition index, 90. If we compare the LED equivalent to the 60 watt incandescent, the best we can do is 80. So the incandescent wins that fight. Lifespan, if ultra high lifespan incandescent, we can get up to around 2,500 hours of operation. The LED way outflanks that by a factor of 10. The LED is up to 25,000 hour equivalent on this standard replacement. On the efficacy, or lumens per watt, again, standard incandescent, really low efficiency or efficacy, only 11 lumens per watt. The LED equivalent is 78. So huge factor on efficiency. The power usage, obviously the incandescent was a 60 watt incandescent, so that's its usage. The LED equivalent is only 9. They were both dimmable. Now on cost, I can still go out and get a 60 watt incandescent lamp for 20 to 40 cents a piece, sometimes even cheaper. LED equivalent, if I get a quality LED, is $4 to $6 a piece, if I get a quality dimmable LED equivalent. On the next slide, we're going to compare an LED equivalent to a 250 watt high pressure sodium that you would typically see in like a high bay area, possibly in a warehouse where color addition index wasn't important, or out in a parking lot. 250 watt high pressure sodiums are very typical in parking lots. So we're going to compare the same categories. On the color rendition index, high pressure sodium, poor. It's not 0 like low pressure sodium, but it's only 22. The LED equivalent, way better. We're up to 80 on the color rendition index. So LED wins that battle. The lifespan, high pressure sodium, not a bad lifespan at 2,400 hours, but the LED equivalent is all the way up to 50,000 hours. So superior life by a factor of 2. On the efficiency, high pressure sodiums are fairly efficient at 116 lumens per watt. The LED equivalent is even higher at 137 lumens per watt. Power usage, that 250 watts, high pressure sodium obviously is 250 watts, where the LED equivalent is 80. Neither one of these lamps are dimmable. The cost of the high pressure sodium is anywhere from $7 to $10. Ooh, this is where the LED equivalent currently takes a beating. Currently the pricing on are $150 to $200 a piece. So you have to look at a combination of lifespan, energy usage, and really run the numbers close. This ends lecture 11A. When you're ready, you can proceed to a lecture 11B.